Okay, good morning. Welcome back to the third lesson. So today we'll revise acids and bases. Okay, so let's have our notes ready. You can find this under the homework folder of your personal folder in our chemistry notebook, right? The homework folder. Now, basically, acids and bases is a small topic as compared to other topics in the pure chem syllabus. However, acids and bases is an important fundamental topic for you to understand other things. Other things like mole concept, titrations, right? Other things like salt preparation, QA, will all rely on acids and bases. Okay, now acids and bases has 6 main parts, if you like. The definition of what is acid, base, and alkali, the concept of a strength of acid, the reactions of acids, reactions of bases, indicators and pH, and finally we end off with types of oxides. Now in today's lesson, we're going to be doing a short summary of some of these things. Okay, while others, I will guide you to where you can revise for them. All right. A good resource that you should revise from is always your notes. So you might want to go back to your acids and bases notes from Sec 3 to go through some of these concepts again. Now we will start off with the definitions, and that's where we begin, and that's where it's very important. So what is an acid? So I'm sure you know by now, acids are substances. So an acid is a substance that dissociates and ionizes. All right. Now, when it dissociates and ionizes, it produces H+ ions. When dissolved in water. So this is the definition of an acid. All right, it produces H+ ions when it dissociates and ionizes, and this occurs when it's dissolved in water. Okay, so what is also crucial is about writing the equations for the dissociation. So the first typical example is HCl, hydrochloric acid, dissociates to produce H+ and Cl- when in aqueous solution. Now, sulfuric acid is interesting because sulfuric acid is a dibasic acid. So many students will write H2+, which is incorrect. It's H+, but it has double the amount of H+. Okay, so in case you are still confused, please ensure you know that it's 2H+. There's a difference between 2H+ and H2+. All right? 2 in front just means it has twice the amount of H+. So we say that sulfuric acid is dibasic, whereas hydrochloric acid is monobasic. So dibasic means it produces 2 H+ ions per molecule of acid. So per molecule of H2SO4, you will produce 2 H+ ions. So based on this, you already know it will have 2 times the amount of H+. Right? Hence, if I have 1 mole of sulfuric acid, I have 2 mole of H+. Okay? And this also works for concentration. If I have 1 mole per dm cube sulfuric acid, it will have 2 mole per dm cube H+. Okay? So it's double the amount of H+ ions. Okay? So this is acid. Then we move on to alkali. Alkali is a substance that dissociates and ionizes to produce OH- ions, so hydroxide ions, when dissolved in water. Okay, So this is an alkali. So the most typical alkali you have learned is, of course, NaOH. Right? Now, so you have learned the definitions for acids and alkalis. Acids is in terms of H plus ions, alkalis, OH minus ions, right? So then we come to the last confusing term, which is base. So we have acid, alkali, then the last one is base. So what is a base? We talk about acids and bases, right? A base is actually a substance, usually a metal oxide or metal hydroxide that reacts with acids to form a salt and water. Okay, so the base definition, the definition of a base, right, is more generic. Okay, it's a bigger general category. It's just basically a metal oxide or metal hydroxide which reacts with acids to produce a salt and water. Okay, so base is the more generic, bigger category. Alkali is a smaller category. In what sense? Base, then alkali is a smaller subset. Why must alkali be a smaller subset? Because alkalis must be soluble. The definition of an alkali requires it to dissociate and ionize to produce OH minus when dissolved in water, meaning it must dissolve in water. So alkalis must dissolve in water, whereas bases can be insoluble. For example, copper 2 oxide is a base. Copper 2 oxide is insoluble in water. However, copper 2 oxide still reacts with acids to form salt and water. Okay, so alkali is a subset of base. So an alkali is definitely a base, but a base need not be an alkali. So what is soluble in water? Group 1 compounds. So sodium hydroxide, potassium hydroxide, cesium hydroxide, definitely soluble. Okay, now group 1 is straightforward. The next one that is soluble that you need to know, calcium hydroxide. And the ones below calcium, strontium and barium. So these three are also soluble in water. Okay, and of course, one more that I've left out is ammonia. Ammonia can dissolve in water. Okay, so these are the three definitions: acids, alkalis, and bases. Okay, so beyond the definitions, let's go on to the strength of acids. So this is an important concept which is in pure chem only. All right, so now we have finished the definitions. Let's go on to strength of acids. Now, what is a strong acid? A strong acid is a substance that dissociates and ionizes completely to produce a high concentration of H plus ions when dissolved in water. So you notice that this definition is quite similar to the previous definition, except for the fact that you need to say that a strong acid is one which dissociates and ionizes completely. So HCl is a strong acid. Because it dissociates completely. So if I have 1 mole of HCl, I will get 1 mole of H+. Okay, when I dissolved it in water. Now that's a strong acid. Then we move on to what's a weak acid. So a weak acid is different because a weak acid is a substance that dissociates and ionizes partially and reversibly to produce a low concentration of H+ ions when dissolved in water. So now that you have learned reversible reactions, you should be able to relate to this more. So take, for example, this is ethanoic acid. So you have just learned carboxylic acids, right? Ethanoic acid dissociates reversibly. So we can see a double-headed arrow being used. It produces H+, and the corresponding ethanoate ion. All right. So carboxylic acids, organic acids, are weak acids. So ethanoic acid belongs to the carboxylic acid homologous series. So ethanoic acid is a weak acid. It will dissociate and ionize partially and reversibly to give a very low concentration of H+ ions. Okay, it is estimated that maybe out of 1,000 ethanoic acid molecules, maybe only 1 or 2 are actually dissociated. Okay, so that's the difference. Strong acid, 1,000 HCl molecules, 1,000 H+ form. However, for ethanoic acid, you're looking at maybe just 2 H+ or 3 H+ at most being formed from 1,000 ethanoic acid molecules. Right? Organic acids are weak acids. Acids, it has to be a carboxylic acid. All right. So alkanes, alkenes, they are organic, but they are not acidic because they do not dissolve in water. They do not dissociate to produce H+. Okay. Now this is ethanoic acid. So carboxylic acids are weak acids. But besides that, okay, please don't go away with the idea that no, oh, so if it's not a carboxylic acid, it means it must be strong. There are other acids which are also weak. Oh, sorry. Okay, so this is H2CO3. This is called carbonic acid. Now, carbonic acid is what you form when CO2 is dissolved in water. CO2 is an acidic oxide. So it will dissolve in water to form acids like carbonic acid. Okay, now carbonic acid dissociates in a two-step manner. This is the first dissociation of carbonic acid. Now HCO3-, you need to know this ion is in your syllabus. It's called the hydrogen carbonate. And another word for it is the bicarbonate ion. Okay, so you need to know HCO3-. So HCO3- is formed when the carbonic acid dissociates and ionizes partially and reversibly in water. Now, this is the first step in the dissociation. The second step involves hydrogen carbonate ion dissociating further to form this. All right, so it's a two-step dissociation. And that's the reason why if you were to titrate carbonic acid with sodium hydroxide, you have two endpoints because there are two dissociations. Okay, so we will see that later. Okay, so it's not just carboxylic acids. There are some other acids which are also weak acids, but they are not carboxylic acids. Sorry. Okay. The equations are balanced. All right, the equations are already balanced. Okay. Now, so now can we please focus on the weak acids? So how weak is weak? We need to have a certain numerical term to quantify how weak is weak, right? Is carbonic acid weaker or is ethanoic acid weaker? So how do we actually do that? Now, we can use a term called the acid dissociation constant. Or what we call Ka for short. So the Ka of ethanoic acid is defined as the concentration of H+, concentration of ethanoate over the concentration of the undissociated acid. Okay, concentration of H+, concentration of ethanoate, concentration of undissociated ethanoic acid. Okay, so that's how you define Ka. Now you don't have to memorize this. This is given to you in an exam. Okay, it's given to you in an exam. However, what's important is you realize that, oh, so this is clearly a ratio, right? It's a ratio of H+ to the undissociated acid. Cause it's H+ over the acid, right? Whenever you see a fraction, you should think of ratios. So what is it then? If the Ka is large, what does large Ka mean? Large Ka means more H+ is produced, right? Higher concentration of H+. So acid is stronger. Right? The Ka is large if the numerator is large. The numerator contains H+ concentration. So if the Ka is large, this means that the acid must have dissociated more. And hence the acid is stronger. Okay? Now, at the same time, if the Ka is large, that means the denominator also small, you know. That means you have less undissociated acid. Okay? That means, oh, the acid has dissociated more. Because the number of undissociated acid left is less. So this is an important concept. Now, this is not the same as pH. It's not the same as pH. The reason is because Ka is a ratio of H+ to the undissociated acid. All right. So Ka measures how much acid has dissociated. So this is a measure of strength of acid. So this measures the strength. Because you actually measure how much acid has dissociated. pH does not have a ratio like this. pH is just concentration of H+. That means I could have used a very weak acid, but used a very high concentration of it. So it still has a lot of H+ because I started with a lot of acid, but maybe only a little bit has dissociated. But yet the pH will still show that it's quite acidic. That's why pH is not a measure of strength. pH is a measure of concentration. Okay? Now we're going to look at Ka values of different acids. So when you see Ka, right, just remember Ka is a measure of the strength of the acid. You should be talking about strong acid versus weak acid, stronger acid or weaker acid. Okay, it's not the same as pH. So later on, we'll do pH, the formula for pH, but it's not the same. Okay, moving on. So in the document, I've given you Kas of certain acids. So the first group of acids, of course, is the most common. HCl, HBr, HI. These are all formed by group 7 elements, right? Cl, Br, and I are found in group 7. So what is the trend in acid strength? Just by looking at the Ka values, what can you say about the strength of the acids down group 7? If you look at the values, the Ka becomes larger down group 7. Right? You went from 10 to the power of -4 to 10 to the power of 6, 10 to the power of 9. So you can tell that Ka has become larger. If Ka becomes larger, that means the acid strength increases down group 7. Okay, this is what the data tells you. All right, so HF is the weakest acid, HI is the strongest acid based on the Ka values. Okay, so that's the trend. But what could be the reason for this trend? So if we recall last year, our end of year exam, we had a question on this. I gave this data and I gave something else, which is the bond energy. All right, the bond energy of the covalent bond. Right, so if you look at the bond energy of HF, HCl, HBr, HI, what is their bond energy like? So this one we will give you in the exam as well. Okay, so please don't memorize this. It's not a memory work test. Remember? But the idea is after I give you bond energy, can you effectively relate it to the acid strength? So let's look at the bond energy now. Okay, I will search out the bond energy in a bit. Just give me a while. The first one, HF is 562. Okay. Now, what do you notice about bond energy? As you go down the group, the bond energy decreases. Now, what is bond energy? You have already learned bond energy, right? Bond energy is the amount of energy taken in to break the covalent bond. So meaning the covalent bond becomes weaker. So you think back, what do you learn about acids? For acids to be strong acids, they have to dissociate and ionize completely, right? If they need to dissociate and ionize completely, what that means is the bond needs to break. The HF bond must break so that the H can form H plus, F can form F minus. The HCl bond needs to break so that H can form H plus, Cl can form Cl minus. Right? So dissociation requires breaking the covalent bond. So if the bond becomes weaker down group 7, less energy is required to break the bond for dissociation. Okay, you need less energy to break the bond as you go down group 7. Therefore, less energy required to break the bond for dissociation. Therefore, it's a stronger acid. Okay. Now, this is a potential question, right? So you have seen it in your end of year exam last year. Okay, if you go back to your end of year exam paper, you saw this is how acids was tested. The entire question was about Ka and bond energy. So we have given you the data, you just need to relate the data together. Okay, so that's the first trend that you see. Okay, so we have seen the trend in acid strength down group 7. Now let's see carboxylic acids. All right. Now, carboxylic acids are organic acids, so they are made up of carbon, hydrogen, and oxygen. Okay. So first we can see, oh, we have CH3COOH. That's 1.75 times 10 to the power negative 5. But once I've substituted one of the hydrogens with fluorine, so instead of CH3COOH, I have CH2FCOOH. By substituting a fluorine in, my Ka becomes bigger. So substituting fluorine in increases the Ka. And what's even more alarming, more fluorine, larger Ka. So if we look at the last one, CF3COOH, this means that you have substituted 3 fluorines in. So you can see that having more fluorines makes the acid stronger. Okay? Can? Now, this is a data-based question. So we will give you the data. You have not learned the reason why. Why is it that more fluorine results in a stronger acid? You have not learned this reason why. So don't bother to fathom the reason. Look at what the data is telling you. The data is just showing you that substituting more fluorine atoms in results in a larger Ka. Therefore, the acid is stronger. So that's the conclusion that you draw from the data, right? Now, for those who have been through the chemistry Olympiad, this has to do with the electronegativity of the fluorine atom. Fluorine is the most electronegative element. As a result of that, having more fluorine atoms in there means you have more electronegative atoms in it. Having more electronegative atoms next to the carboxylic acid functional group makes the acid stronger. Okay? Now, moving on, how does the strength of an acid affect the speed of reaction? So you have seen this graph before. This is basically the volume of gas against time graph. So very often, acids can react with different substances to produce gases. So in this case, it's hydrogen gas. Hydrogen gas is produced when acids react with metals, right? Acid plus metal forms salt and hydrogen. Okay. Now, besides hydrogen gas, acids can also produce carbon dioxide gas. When acids react with carbonates, acid plus carbonate forms salt, carbon dioxide gas, and water. Okay. Now, this is what happens when you use 0.1 mole per dm cube HCl. Now, HCl, I'm sure you remember, is a strong acid. So strong acids dissociate completely. So what that means is if you have 0.1 mole per dm cube HCl, the concentration of H plus is also 0.1 mole per dm cube. Now, this is HCl. But what happens if I were to use a weak acid instead of HCl? Take, for example, instead of HCl, I use ethanoic acid. 0.1 mole per dm cube ethanoic acid. 0.1 mole per dm cube ethanoic acid. It's a weak acid though. If it's a weak acid, will all the ethanoic acid dissociate to produce H plus? The answer, of course, is no. Right? A weak acid is defined as an acid, a substance that dissociates and ionizes partially. This means that the concentration of H plus is lower than 0.1 mole per dm cube. This means that the concentration is not 0.1, it's lower than that. And we have learned, right? Lower concentration means speed is slower. Because speed of reaction is affected by concentration of the reactant. In this case, the reactant is acid, H plus. So if the concentration of H plus is lower, the speed is slower. Slower means the gradient is less steep. Hence, your ethanoic acid graph must look like this. The gradient is less steep. Okay, let me draw it nicely. So you start off at 0, less steep. But the question now is, does it end off at the same volume at the end? Remember, the volume at the end depends on number of moles, right? Number of moles of the ethanoic acid. Okay? The number of moles of ethanoic acid is the same because you had used the same concentration of ethanoic acid. The CH3COOH is 0.1 mole per dm cube. So the number of moles will also be the same and it ends off at the same volume. Okay, so this is what happens when you use 0.1 mole per dm cube ethanoic acid. The only impact is that the initial speed is slower. And that's because the concentration of H plus is lower. But the final volume is not the concentration of H plus. The final volume depends on number of moles, which is the same. The number of moles of the acid, that is. Okay? This should be familiar to you. This was one of the speed of reaction TYS questions. Okay? Now, this is what happens when you use a weak acid. The speed is slower, but if the concentration of the acid is the same, you should still have the same final volume of gas. But let's challenge our understanding further. What happens if instead of ethanoic acid, I had used sulfuric acid? So what happens if I use 0.1 mole per dm cube sulfuric acid? Now, sulfuric acid is strong, right? But beyond being strong, sulfuric acid is a dibasic acid, meaning my H plus concentration is not 0.1, My H plus concentration is 0.2, is double, which means the speed should be faster. And the final volume should be double. Okay? So that's the difference between a dibasic and a monobasic. There's a difference between a monobasic strong and a monobasic weak acid. Okay, so this is a quick consolidation of what you have already seen under speed of reaction if you have done the TYS. Okay. So hopefully you have seen how strength of acids can affect the speed of a reaction, how it can affect the graph of the gas volume against time. Okay, so all these have to do with strength of acids. Okay. Now, strength of acids is about whether the acid dissociates completely or partially. Now, moving forward, we are going to talk about a different concept, which is pH. Now, pH has a formula. Now, in general, when you see this in chemistry, when you see P in chemistry, a small letter P in a mathematical formula, it means negative log base 10. Okay, so this is the formula for pH. Now you realize that pH only measures one thing, which is the concentration of H plus. All right, is the concentration of H plus. It doesn't have any other terms in the formula. It doesn't have the concentration of the undissociated acid. It is just concentration of H plus. So what happens when, let's say, you have 0.000001 mole per dm cube HCl? What is the pH? So you can rewrite this. This is 1 times 10 to the power of -6. So if you use your logarithms, negative log base 10, 1 times 10 about -6, you get pH 6, you know. Does it mean that pH 6 means HCl is a weak acid? pH 6, okay, maybe I should write it now. pH 6 does not mean HCl is a weak acid. What it means is the concentration of H plus is very low, dilute. So what you have seen is HCl is a strong acid, but if I diluted it enough, the pH becomes higher. That's it. Okay? So similarly, I could have used a weak acid, but I concentrate it. Then the pH is lower. Okay? So pH doesn't tell you whether something is a strong or weak acid. It's only a measure of concentration. Having said that, but if concentration of acid is the same, for example, 0.1 mole per dm cube HCl, 0.1 mole per dm cube ethanoic acid. So if you compare like for like, same concentration, then the pH will tell you what the strength of acid is. So a weaker acid has a higher pH, a stronger acid has a lower pH if the initial concentration of the acid is the same. Okay? So with that, we have covered pH. So pH doesn't measure strength of acid. pH measures concentration of H plus. However, if the concentration of the acid is the same, then the pH reflects to you the strength of the acid. That's why you learn in Sec 2, right? Vinegar contains ethanoic acid. Vinegar has a pH of about 3 to 4. Whereas hydrochloric acid, pH 1. This is what you memorized in Sec 2. But now you see why. It's because if I were to compare the same concentration of HCl and vinegar, HCl has a lower pH because HCl is a strong acid. Vinegar is a weak acid. Okay. Now, moving on. So we have covered strength of acids. We have covered pH. The next one is on the reactions. Now, this one I won't spend too long on the reactions. I'm sure you know by now, acids can react with a few things. Base is one of them, from salt and water. Now, just to repeat, base doesn't need to dissolve in water. A base is just a metal oxide or metal hydroxide. Okay, so like copper 2 oxide is a base. Copper 2 oxide doesn't dissolve in water, right? Okay, those that can dissolve in water are called alkalis. So like sodium hydroxide. Sodium hydroxide is a base, but it's also an alkali, right? So whenever we say base, base is the bigger subset. Alkali is the smaller subset of base, okay? Yes, not all bases are alkalis. Alkalis are all bases. So that's what you all learn set theory, right? Base is the big category. Alkali is the subset. That means all alkalis are bases. However, not all bases are alkalis, right? Okay, so this is why you learn set theory. Okay, now besides bases, acids can also react with metals to form salt and hydrogen. Acids can react with carbonates to form salt, CO2, H2O. Okay. Now, these are the three reactions. Now, how do you differentiate between bases and alkalis? You can differentiate between bases and alkalis just by looking at whether they dissolve in water. If the metal oxide or metal hydroxide can dissolve in water, then it's an alkali. Okay? Can? So these are the three reactions of acids, which I'm sure you know by now. Okay, so now after the reactions of acids, we should know the reactions of bases. Now, bases react with acids, obviously. That's the first one. But besides that, bases can react with ammonium compounds. If you warm a base with an ammonium compound, it produces a salt, ammonia gas, and water. All right? So that's how you produce ammonia gas, when the bases react with ammonium compounds. Okay? Now, this is a quick revision of all the reactions. So now we move on to indicators and pH, which is where we look at the titration curves, which is inside the document itself. So I've given you a few titration curves. We're just going to look at each one of them in turn and look at how the strength of the acids and bases used in the titration would affect the titration curve. Okay? So before I move on, can I just check that you are familiar with the 4 reactions that I've listed down here? Okay, we have finished copying. Can you please give me a thumbs up? Yep. Okay. Okay, so titration curves. Now, titration curves basically measure the pH change as acid or alkali is added. Okay. So in this case, you can see my first titration is a strong acid, strong alkali, or strong base titration. All right. So for example, HCl and NaOH. If I titrate HCl and NaOH, this is how the pH will change. At first, it's HCl, right? So HCl has a pH that's less than 7, right? So this is less than 7. pH less than 7 means acidic. So that makes sense because at first it's HCl, it's acidic, but you're starting to add NaOH to it. As you add NaOH to it, the pH starts to increase little bit by little bit because the NaOH neutralizes the HCl. Okay? However, you notice that the pH doesn't change suddenly at the start. At the start, the pH changes gradually, which is also your experience with the titration, right? At the very beginning of a titration, actually nothing much happens. Nothing much visible happens to your eyes. Even though there is reaction happening, you don't see it. The indicator doesn't change color. But all of a sudden, as you near the end point, you must get very, very careful and add your alkali drop by drop. The reason is because there comes a point whereby the pH changes suddenly. And you can see this from the graph. The pH shoots up almost vertically. So this point is where the titration is complete. So the titration is complete at this particular volume of alkali. Okay. Now, what is the pH at this point? Now, this is called the end point. Another word is also called the equivalence point. Generally, we will take the midpoint of this segment. The midpoint of this segment tells you the pH at the end point. So if I use a strong acid, strong base titration, the pH at the end point is 7. Okay? The pH at the end point is 7. Okay? Next, in every titration, you must choose an indicator, right? So just like in the lab, you have done a number of titrations, all right? You must choose an indicator that changes color at your endpoint. You must choose an indicator that changes color at that range of pH where your endpoint occurs. So where does your endpoint occur? It occurs from about pH 5 to pH 9. The midpoint is 7, pH 7, but the pH changes from pH 5 to 9 very suddenly. All right? Generally speaking. That means wherever the pH, the indicator changes color must fall within this pH range. All right? Now, this is a strong acid, strong base titration. So HCl, NaOH, or sulfuric acid, NaOH also works. Now, what happens if I now titrate a weak acid versus a strong base? Immediately, you see the first difference. And this is the first difference. The pH is more than 7 at the endpoint. If I use a weak acid, strong alkali and titrate them together, the pH is more than 7 at the endpoint. Now, weak acid is like ethanoic acid, strong base is like NaOH. So if I titrate ethanoic acid with NaOH, this is what I see. Okay? So you can see your indicator that you choose for this titration must change color from pH here to here. So it's about 7 all the way to 11. All right. Now, this indicator is usually phenolphthalein. Phenolphthalein. Okay. So very often we will give you different indicators, data about different indicators, and ask you, oh, it changes color from this pH to this pH. So choose an indicator suitable for the titration. How you choose? You got to choose an indicator that changes color in the range whereby the pH shoots up. It shoots up from pH 7 to pH 11. So your indicator must change color somewhere in this range. Okay? So this one don't need to memorize. The data is given to you again. But again, you need to know how to choose. Your basis for your choice must be, where does the indicator change color at? The indicator changes color at the pH where the pH shoots up. Okay, you cannot choose an indicator that changes color at pH 5. It wouldn't work for this titration. Okay, moving on. What happens if you have strong acid, weak base? So again, this is the reverse. You can see, oh, the pH at the endpoint is less than 7. Okay, and you can see the indicator must change color. At pH 3 to about 8. So typically, this one we will use Meta orange. Okay. Now, you don't have to memorize this, but the idea is, if I were to give you the titration curve, can you tell me these 2 points? If you can, then you have understood it. So you would have seen this in a number of schools papers. So if you have done the school papers, as well as your TYS, this was a database question for one of the years, where they give like 3 titration curves. Okay. And the students were asked to do more concept on it. The students were asked to suggest what indicator to use, and so on and so forth. All right, so this has come up before in the TYS as well as the other school papers. Okay, moving on to the very last part of today. Now, the last part of today is not really for us to go through in detail, but I hope you also know just now what I mentioned about dibasic acid. So carbonic acid, H2CO3, is carbonic acid. Now, carbonic acid has 2 endpoints. Because carbonic acid is a dibasic acid, right? Dibasic acids typically have 2 endpoints, especially if the dibasic acid is a weak acid. If the dibasic acid is a weak acid, like carbonic acid, you will see 2 endpoints. And the 2 endpoints is because, of course, you have 2 different dissociations. The first dissociation is this one. H2CO3 becomes HCO3 minus plus H plus. The second dissociation is this one. The HCO3 minus dissociates to form CO3 2 minus and H plus. Okay, so because you have 2 endpoints, the graph looks like this. And because of the 2 endpoints, typically, we will use 2 different indicators for the titration. All right, so just for your information, a dibasic acid has 2 endpoints. Okay, and the graph looks like this. Now, this graph is commonly found in dibasic acids, which are weak acids. All right, typically you will see such a graph. Now, the final part of this chapter, so we have covered everything, including pH and indicators. The last part is types of oxides, which I hope you sincerely remember. There are 4 types of oxides. We have the first one, acidic. Then you have basic. Then you have amphoteric. And finally, neutral. Right, so 4 different types of oxides. Now, another way to say types of oxides, the question can say nature of oxide. When we say nature of oxide, we really mean whether it's acidic, basic, amphoteric, or neutral. So acidic. Acidic are non-metal oxides. For example, CO2. CO2 is an acidic oxide because it dissolves in water to form acid, carbonic acid. SO2, acidic. NO2, acidic. All right? And so on and so forth. So long as a non-metal oxide, non-metal oxides are acidic. Basic is the reverse. Basic are oxides formed by metals. MgO, magnesium is a metal, sodium oxide, copper 2 oxide, and so on. You notice they need not dissolve in water, right? Bases need not dissolve in water. But these will react with acids. Okay? Now, before we go on to amphoteric and neutral, acidic oxides are acidic. This means that they react with bases only. All right? Acidic oxides can only react with bases. Basic oxides react with acids only. Okay? So your basic oxides cannot react with bases. Basic oxides must react with acid. Okay? Finally, we go to the last two. Now, the last two, it's better to memorize which oxides they are. Amphoteric, there is zinc oxide, aluminium oxide, and lead-2 oxide. Zinc, aluminium, lead. Okay, can I add one more? Chromium 3 oxide is also amphoteric. All right, chromium 3, yeah. Okay, you must say 3 because chromium is a transition metal, so it has variable oxidation state. So you have to specify. It's chromium 3 that's amphoteric. Amphoteric oxides react with both acids and bases. Okay? So amphoteric means both. That's the reason why when in QA, you added NaOH to a solution containing zinc ions, it forms zinc hydroxide. Zinc hydroxide can dissolve in excess NaOH because it reacts with NaOH. And that brings us to the idea, it's not just oxides, right? Hydroxides also follow a similar rule. Okay? So the hydroxides can also be described as amphoteric. So zinc hydroxide is amphoteric, aluminium hydroxide also amphoteric. Okay, and finally, neutral. Now it's better to memorize again which ones are neutral. Water is the best example. Water is definitely neutral. Water has a pH equals to 7.00. Okay. Carbon monoxide, neutral. Nitrogen monoxide, neutral. Nitrous oxide, another oxide of nitrogen, also neutral. You notice that they are all monoxides. Okay, they only contain one oxygen. Okay, and they are all monoxides of non-metals. Okay, so because they are neutral, they do not react with acids or bases. Okay, and those are the 4 types of oxides, which you should be familiar with because this is important later on for QA. Okay. Okay, and with that, that brings us to the end of the revision for acids and bases today. Thank you and hope to see you next time where we will revise salt prep and QA. Okay.